Hi, welcome to Interact and Learn. Today we are going to study about the hybrid pi equivalent model for BJT. Why do we need such a model? When you see the symbol of BJT in a circuit, is it difficult to visualize how it works? A model helps you understand what is the electrical equivalent of the device and how you can break its working in terms of simple currents and voltages. As shown in the figure, we can assume the device to have two ports. A port is any point of the device which one can interact with. The input port consists of the emitter and the base. You can feed an input signal to the base of the BJT. The output port consists of the collector and the emitter. The collector signal can be viewed on a CRO or can be fed to another stage. Building on this, let's analyze this two-port network, namely BJT. Let us start by analyzing the input port first. If a small AC signal is applied at the base, it leads to flow of current IB, which in turn produces a potential difference between the base and the emitter called VBE. Notice that the letter as well as the subscript are in lowercase, denoting AC quantities. VBE and IB can be related using a small signal resistance called R pi. It is this resistance which will represent the input port of BJT, and we need to find its value at quiescent point to be able to calculate it. At Q point, R pi is simply equal to any small change in VBE over any small change in IB. Notice the subscripts. VBE and IB are AC plus DC quantities. The subscript is in uppercase denoting DC and the letter is in lowercase denoting AC. Why AC plus DC? Because the transistor is powered up using VCC, which is DC, and the small signal applied to the base is AC. In order to simplify the differentiation, we express the equation in terms of 1 by R pi. Now, as we all know, IB is equal to IS by beta into exponential of VBE by VT at the Q point, where IS is the saturation current, beta is the current gain, and VT is the thermal voltage. We can replace IB in the previous expression with this equation. Upon differentiation, 1 by Vt comes out as a constant. As we see, the rest of the expression is nothing but Ib at the Q point. At Q point, the lowercase I and the uppercase b can be written as capital I with subscript capital BQ. This is the DC value. Why? Because when you differentiate AC signal, you get the value of the signal at a particular point, which is not time varying, a characteristic of a DC signal. Thus, R pi is equal to Vt by IBQ, which is equal to beta Vt by ICQ. Here, R pi is called the base emitter input resistance or diffusion resistance. It is called a diffusion resistance as it is the resistance offered to the carriers when they try to diffuse from the emitter to the base. Now we are ready to replace the input side of the BJT with its equivalent electrical network. Current IB flows creating VBE across resistor R pi. Let us analyze the output network. IB leads to VBE, which in turn leads to collector current IC, which in turn causes a voltage drop across the collector emitter junction called VCE. IC can be analyzed in two ways. It depends on VBE and in turn depends on IB. Let us first analyze IC in terms of VBE. IC at a particular point can be found using the displayed equation. But we know that IC is also represented by IS into exponential of VBE by VT. Replacing this equation in the expression, we get the displayed equation. Differentiating with respect to VBE, we have 1 by Vt as the constant. This gives us that IC is equal to ICQ by Vt into VBE. ICQ by Vt can be termed as transconductance Gm. It is conductance as it is the ratio of current upon voltage. As we see, IC depends on the input side voltage. Hence, in the equivalent model, we will have a dependent current source. The output network can be replaced by a current source with value GMVBE. It is controlled by the input voltage and hence is marked as a dependent current source. The entire electrical model now looks like this. If you look from the emitter end, the equivalent circuit looks like a pi. Hence the name pi model. Why hybrid? Because the equivalent model has both voltage and current. Hence the name hybrid pi model. Had it been just voltages, we would have called it the impedance pi model, and had it been only currents, we would have called the admittance pi model. In yet another way, as discussed before, IC can be analyzed with respect to IB. Any small change in IB causes a change in IC, which is represented by beta, the common emitter current gain. IC is equal to beta IB. This is a current dependent source with the value beta IB as shown in the accompanying figure. Instead of GMVBE, we have beta IB, which yields the same current IC. The common emitter current gain beta is nothing but ICQ by IBQ. Multiplying and dividing by VT, we get this expression. The first term is nothing but R pi and the second term is nothing but GM. Thus, the common emitter current gain is equal to transconductance multiplied by the diffusion resistance. The story behind the hybrid pi model. This model was developed by Lawrence J. Giacoletto. He worked at Ford Motors before he started teaching at the electrical department of Michigan State University. In 1969, he developed the hybrid pi model. He was known to be a very strict professor and was nicknamed One Pointer Giacoletto as his exams were very difficult and students would rarely get above 1 point when they took his exams. That is all for this session. Hope you enjoyed it. Interact and learn. Cheers to learning!